All right, everybody, welcome to week 4 of computational physics. This is the Wednesday class, but since I do one class recorded, and it should be on HyFlix right now, but I can't check it, so if you've got a question, you've got to pipe up. So today we'll talk about, just in case you missed all this, we'll talk about essentially operations. So we talked about NumPy arrays, we talked about NumPy random, how you can seed an array, and we did some basic statistics. We're essentially already doing some operations, but we can do more things to NumPy arrays. NumPy arrays is what Python speak is for data, and so you'll be working with data undoubtedly in your life at some point, sometime soon in the future. So we'll talk about what you need for the 4th Jupyter Notebook assignment: casting, sorting, matrix operations, and the simplest file I/O, meaning input, output. So operations are to modify an array, to compute array's characteristics, or to return array identifiers. So you can do a computation and simply say, this is where this is true in your array. So it doesn't actually modify the array itself. It just returns an array with true and false statements. We saw this with where, NumPy where, for example. All right, so an array, a NumPy array is a list of numbers, strings, or any kind of available type. So we don't particularly care what's in there. That's just the data. We are now going to see what we can do to set data. For example, a data sample or a time series. That time series is one of my favorites because you basically you instantly have time and measurement. Time, measurement, time, measurement. Very typical for any kind of physics, right? So NumPy arrays can be multi-dimensional. So that's a essentially two-dimensional array already. That's a table. And most of the time, you'll be working with tables. Possibly, you'll be working with three-dimensional arrays, which is an image over time, for example. That's a data cube. So that's usually the end of the number of dimensions that are going to get thrown at you. You can either have a single dimension, which is a list of numbers. That's the simplest array, right? A two-dimensional, two lists of numbers right next to each other, like a time series, so time and measurement. And so that has the first dimension is 2, and the second dimension is however long your time series is. And then the third dimension can be, for example, where instead of having a single measurement at a given time, you just take a picture, which is a two-dimensional array, and then take that over time. And that's your third dimension. So how exactly is that cast into your NumPy array, right? So what's the first dimension? What does that stand for? What's the second dimension? What is that? What's the third dimension? And so you want some basic values of that instantly. So as soon as you get a data file of some description, you have to go and ingest it. You have to then go figure out what the mean is, what the standard deviation, what the length of it is, what the dimensions are. That's what operations are for. So you can totally do more sophisticated stuff. And I'm just pointing you to SciPy, Pandas, et cetera, et cetera. But we're going to get started using just, bye, cicada. That was slightly terrifying. OK. So how do you get array properties? You get a wild array. You see this in your data file. I'm just going to go straight through. Well, I'm not going to edit the cicada out. So you can find the numbers of dimensions. You can find the shape of the array, the size of the array, and the size of the first dimension, for example. So we already encountered len as the length of a list. And so you can throw in an array in the same way, just say array len, and it'll give you back the first dimension's length. So for example, if you've got that time series, you'll get the number of columns that you've got, the length of the number. So that's one dimension that you can get, but you probably will go for the shape, because that tells you also how long the time series is. So an array.shape, or just say NumPy shape of this array, will return the numbers of the lengths of each dimension of your array. This is useful because suppose you want to add two pictures together or you want to add two things together, you have to figure out if they're actually the same size. They're actually the same shape. So properties of arrays. So these are the first operations that you can do just to figure out what your data looks like. But you can also see them yourself, right? So we already talked about these, but the zeros, ones, and empty are really useful if you just need to come up with artificial data. Artificial data can start with like, I'm just going to fill it with zeros, and then I'm going to assign values to it. But I'll give it like, I don't know, two dimensions, time series, and value, and then 300. I'll just do this for 5 minutes, and so every second, and so that's how many. That's what my dimension should be. Or I can do this with ones. And importantly, there's one keyword that I use a lot, which is D-type, which basically says this is the type you should be expecting. D-type equals float means it is a number with a precision more than one, at least one after the period. So you actually have one significant number, 1/10 or 100th. You can also say int. These can only be integers. Or you can say string or whatever, but it's like that's where you actually specify this is what you should expect. You can also do empty, and it simply has nothing assigned to it. So zeros and ones, I mean, you can do ones equals string, so then you have an array filled with ones between quotation marks because it's really a string. I do not recommend that. That's what empty is for. If you want to just fill it with strings, then you say dimensions and D-type is string. So this allows you to quickly allocate some memories, like to say, like, okay, this is the array that I want, this is the shape that I want, and then you can check it with the previous slide with these. You check it with the properties, right? So did I actually assign it properly? Conditional arrays is when you start saying, okay, numpy where or is none or is inf basically gives you those true values. It evaluates an array. So it has like, here's my data, evaluated whether or not there is not a number in there. So if I have assigned not a number somewhere, or if you've measured not a number somewhere, it returns whether that is true. And if it's infinite, I have accidentally divided by 0, it will remember infinity, and it returns the indices where that is true. That is useful to know because if you're computing, for example, the mean or the standard deviation, you want to take those two out. You want to take the not a numbers and you want to take the infinities out because otherwise it's going to be all skewed. And numpy where is a good way to, for instance, slice your array and say like, all right, well, I want all the values where the temperature was below freezing. And so that'll go numpy where t data, the column that equivocates the temperature, is below 0 Celsius, for example. You can't use units just yet, so you have to remember what your units in your numpy array are. So masks can return an array with true or false values. They can use one or more conditions to be met, and it's great for selecting subsamples. So numpy where returns the indices where a condition is met. That's another way to find a subarray. Instead of having like the full array with true, false, true, false, true, false, you can actually have it's just true for these arguments, like the indices where this is true. So that's not numpy where, it's numpy arc where. Difference is that a mask of the same length, and so that's easier to use, and you can also just select the indices. That's another way of going through it. Why am I doing all these operations? The reason for these operations are that they are hard-coded into NumPy and therefore work a lot faster than my if loop. I can totally go through a for loop and with a couple if statements and do the exact same thing, and you can do that. You can say the exact same thing as the where statement, but you'll notice that you'll take a performance hit. And maybe that's not a big deal if you only got 20 values, but it will be a big deal when you've got 20 million values. All right, so matrix operations, right? So you can do a matrix like this, multiplied by a vector, and you get a new vector. This is obviously an XKCD, because that's not how vectors work. And so you can do things like addition. So you can say, OK, my A array is this. And notice that we basically defined it using numbers, right? So this is essentially, here's a list of two numbers, here's a list of two numbers, and this is a list of two lists. And that it makes an array. So it makes a two-dimensional array, right? So you've got 2 dimensions in each row, and you've got 2 rows. So that makes 2 dimensions. And you do the same thing with B, and you can add them together because you do element-wise addition. This is super easy. Basically, the things like plus or minus or divided by are what are overloaded. So usually you think of plus as 1 plus 3 equals 4. You know, that's just one number plus another number is a third number. So that's how we think of plus, but you can do that also with matrices. So as soon as you define them as NumPy arrays, Python goes, well, I know I'm allowed to add arrays, so you just need to use a plus. So that's useful, and it actually takes, you know, every single, like this one corresponds to this one, those 2 added is 11, those 2 added is 1, those 2 added is 8, and those 2 added is 0. So you get the actual the addition of the 2 arrays. This can be useful if you want to have like 2 measurements and you want to quickly figure out what the average difference is. So you can use these things. You can use the dot product. So, oh, that's great. So NumPy, you can actually take array A dot B, and that'll give you a new array. So notice how that dot product works. It's a little odd syntax, but he's like, I can take array A dot B, and then you'll get a new array, and so that's the dot product. And so you can do things like transpose, which is really nice. If you have, if you have an array like this, you're like, I don't need it's not a lot of work to transpose this, but it is super handy if you have much larger matrices, right? So these matrix things can become quite handy if you are doing large calculations on big arrays. So this exists, so those are the kind of operations that we can do. So NumPy matrix, the built-in functions are, and so you don't even have to do sum matrix here. Basically, NumPy says, oh yeah, sum is already in me. NumPy does diagonal is a matrix-specific thing, so you can actually get the diagonal values of a big array. But sum is, for instance, something that I use a lot. For example, I'm taking an image and I'm going, oh, I just want all the values above a certain one, the ones that I trust, and then I want to sum them together. And so NumPy sum is how you can add all the elements in an array. So here's a little thing that actually is pretty neat. You can take the array, but you can also say axis, or you can basically give it the direction. And so axis 0 goes like, I'll sum just in that array. So you actually collapse the whole array into one vector, one single dimensional array. And so you can collapse a multi-dimensional array using sum, saying, I want to sum in this direction. So suppose you have you've took a time series of pictures. Click, 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 right? And then you go, oh, you know what? I'm going to sum along the time dimension. So you say sum axis equals 2, because it's like 0 axis 0, axis 1, axis 2. So axis 2, I'm going to sum along the second axis and just sum all those images together. And I'll end up with a stacked image, right, where everything has been added together. That can be useful for diagnostics. It can also be useful to see like really faint things. So sum is a very useful NumPy matrix operation. You can also use mean, standard deviation. You can use min or max. So the min or the max are the minimum, the maximum value. And so all these things are useful when you're doing statistical tests on your data. You can do things like return covariance matrices. Yay, that's really important for error estimates. So matrix operations are useful. They sound like, oh, I'm just going to use this in a higher math class. In fact, you're going to end up using this or very similar things in data analysis a lot. Especially, for instance, if we are doing something called principal component analysis. That is essentially finding the eigenvectors of a n-dimensional data set. If you didn't have quantum mechanics, eigenvectors are basically saying these are the dimensions of the set, and these are the independent values, independent parameters. So basically, I always think of it as like, here's a cloud of points, and it's like, oh, it turns out it has 3 dimensions. All right. So matrix operations, there's always an XKCD for something, so I hope I don't suck at explaining. XKCD certainly does. Doesn't. Typecasting. All right, we talked about this last week. Turn an array from one type into another. This happens a lot because, especially if you read in with AstroPy tables or pandas, you read in a table and it misread it because it just made its best guess. So it says, oh, yeah, these are all strings. And there's no good reason why they're all strings. It just, I don't know, it saw a white space in one of the entries and then went, oh, God, it's all strings. So it sort of defaulted to strings. You go like, no, these are floats. Just please interpret them as floats. So that's when you cast them into from the array of strings into an array of floats. Use with caution. There's a reason that they were assigned strings, right? So I said a white space, and a white space is easy to ignore. If you're converting a float plus a white space, which is in a string, into a float, it will just ignore the white space. But if there was another character there, or there's an accidentally there's an extra dot, or there's an extra comma, or something like that. So this is that will mess things up, and it will just do it. NumPy as array, NumPy as type, and NumPy array into another type. So you can actually just cast one array into another. This is useful if you, for whatever reason, your collaborators has saved everything as strings. I don't know, he's just mad. And he saved everything as strings. And you go, but I want the actual values. So you can actually turn it into values. So all is not lost if it's all in strings. All right, sorting. Now this is the thing that is the kind of like operations that we're here for, right? We have a pile. It needs to be sorted from shortest to longest, right? Wasn't that a fun exercise at high school when we were trying to figure out who was the tallest, who was the shortest, right? And everybody line up and keep swapping with the person left to you until the person left to you is taller than you, and the person to the right of you is maybe smaller, but definitely the person to the left of you is bigger. So sorting returns a sorted array. NumPy arcsort leaves the array alone, just says, yeah, you need to hop through the array in this order. So here are the indices, right? So start with number 132, and then number 2, and then number 8, and then number 22. Those are like, I'm now going in order, just hopping through the array. So it gives you the arguments rather than the actual sorted array. The latter is useful if you want to sort other arrays. So for instance, the column. So you can sort using one column, but you use the indices to, for instance, grab them out of a different column. That can be really useful. Sorting algorithms are not the same. So let's see if this plays. Yeah, so we have we randomize our set, and this is called bubble sort. So I'm going through it like it goes through one direction and kind of takes the value and next one and next one and next one. So it keeps going through, and you can watch how many comparisons there are and how often it had to access the data. So these are two things that actually identify how fast arguments sort. This is a cocktail shaker. It goes back and forth, right? So there is different ways that you can run through your data and sort it. And so you can kind of keep back up here like how many comparisons and how many times you had to access the data. If it's a huge data set, this becomes important, right? So if you have to do lots of comparisons, do I have enough computing power for it? If I have a big data array, like do I have enough storage, but also like it slows down every time I have to access it, right? So if I do something that, yeah, I have plenty of computing power, but I'm limited by how fast I can get to my data, that's the kind of thing where different sorting algorithms become important. So you can see how the differences go. You can see how it goes through data sets, right? This is odd-even sort, where it starts sorting locally and then, there you go. Or shuffling, like there we go, new randomized selection, right? So it goes throughout it performs operation on the entire data set in one go, rather than compare. So there's different double selection sort, goes even faster. Shuffling again, and then insertion. So it inserts where it needs to go. Like it grabs the next value and inserts where it needs to go. It goes pretty quickly. But you can see in the top corner there that they each have different requirements for how many times, how quick you can get to your array and how many computations you need to do. Sometimes you have a big computer, you have like a pile of GPUs, and you go like, I can do tons of computation. That's not the problem. It's getting to the file. That's called I/O limited. So look how many different kinds of sorting algorithms there are. This was basically computational science in the 80s. Like, how can I sort big arrays quickly? And what are the choices I should be doing? Like here, I'm just doing lots of passes over the data, and I just kind of refine. But notice that I had something usable. I could get a mostly pink area very quickly. So I could go, well, if I just need to sort in mostly pink, mostly red, mostly yellow, and I don't quite care how well sorted those are, this might be a better algorithm. So there's all these different arguments for different sorting algorithms. At this point, maybe we are not so fussed about it because we have more computing power. So you can always throw more computing power at the problem. But there's also the thing called, there's always more data that's going to crop up. So being efficient at these things helps. So here's another one where we basically do localized sorts first, and then sort the sections and then do it again, shuffling again. Notice how many of these things there are. Everybody came up with a different sorting algorithm. Everybody tried to figure out how to, so it does localized and then basically does a pass, localized and then does a pass, localized and then does a pass, and eventually last pass, there we go. So it's, and these things all have pros and cons. I've forgotten how many there are. So do we have a lot of NumPy array sorting algorithms? We have a few. You might actually have a few others in other subfields. Usually NumPy sort will just do it. It's quick sort. It just does it for you. You don't have to wait that long. But you may have to dig into a different sorting algorithm, or basically give it a different option, as like use this algorithm versus other, and that might end up saving you some time, especially when you are expecting to sort lots of data files over and over again, and you notice it's taking you a long time. This is the kind of thing where you can start digging through the literature and see what kind of different sorts there are. I mean, there's Tim sorts, so clearly some character called Tim wrote this and wanted to be immortalized forever, but essentially they all end up with the same thing. You all end up with the same sorted range. It just takes different amounts of time and different amounts of computations and different numbers of times that you have to touch the data. All right, I think this might be the last one. But notice that that there's different strategies how to sort, right? And boom, there you go. Is it on a loop? Wikisort. I think I'm done with this because it is a long list of different visualizations on how to sort, right? We'll talk about data visualization starting next week, and I want to note that this is just a rainbow, but it really neatly shows how the different algorithms are sorting and what randomizing looks like. So I have a next one where I'm sorting through another data set, but it actually shows you how fast it's going, although this pretty neatly shows how fast it's going. And do the whole thing. There you go. And clean up. That should be the last one. Grail sort. All right, there's too many to count, really. And notice that how some of them get them sort of sorted fast, and some of them, it depends on how organized it is, right? So sort with different algorithms. So you can do random. Here we go. So sorting here is go through, and you can do merge sort, where you basically go, you start sorting in smaller piles. I think of this as like a group activity, right? You go like everybody gets a bunch of Legos and to sort them into size, and everybody does the localized first, and then you compare, and then you fit them in the right ones, for example. Quick sort is the one that is used by NumPy the most. So that's the default. And notice that some of them, if you have a random array, some of them take a much longer than the others, right? Quicksort wins. Quicksort is a good compromise. So if you have a completely randomized data set, Quicksort's fine, right? That's great. And so that's the thing that you usually get. But data is never always perfectly random. In fact, we're looking for patterns, right? So patterns are our thing. And so a completely random set of numbers is not something that you typically get. All right, we're done. And so with a few unique values, right? So there's only a few unique values. Sort, 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 sort. Quicksort is done first. Great. So if you only have a few values that are possible, people hated the class, loved the class, and meh, those are the two options. Quicksort will sort them into 3 piles very quickly. But notice that the different algorithms, the rest of the algorithms, some of them are still struggling, some of them are not, are done already as well. Again, Quicksort did pretty well. The reason that we use Quicksort as the default, because those two instances are already a good example. And so things like the cocktail sorts or the bubble sort, they take forever, right? This one has to go loop through the whole thing over and over again. This one just keeps going back and forth, like I think it's called a cocktail sort because you're going back and forth with everybody's order. I think that was the idea. And so you have these different sorting algorithms, but you can have, so you have it reversed, right? So I have it actually in reverse order. So flipping it would be the quickest way to sort it. But how do I sort it quickly? Quicksort 1 again. But heap sort is very quick. Bubble sort and cocktail sort seem to just struggle with this stuff. And so it depends on how often you have to move it, how often you have to compare to its neighbors. So some of them just take a long time. But notice that they take different times for different kinds of data sets. All right. In fact, some of them take so much time that I have to fill it with words. And so sorting data will be a thing that you'll end up doing. And especially if Quicksort starts to look like it's really struggling, maybe one of the others might be a better compromise for you. It's not necessarily something you have to go do immediately, but it is something to keep in mind that there is more than one way to sort a heap of numbers. Although obviously none of us are going to be a fan of bubble sort or cocktail sort because that's just a way to have it compile or have the thing run longer. Because you have to keep going through every remaining part of the data over and over and over again and keep comparing it to everything. All right, almost sorted. This helps. Look how quick insertion sort solves that one. Faster than quicksort. It's called quicksort, but not always is the quickest way to sort, right? So notice how quick insertion sort did it like that. So it's the kind of thing where if you suspect that you have a large data set, it's like, they're actually almost in order. There's just one or two that are maybe misaligned. Insertion sort will sort it out for you quickly. Haha, sort it out. So there are different ways to sort data, and it depends on what kind of data you get. Like this kind of example would happen if you merged everything together and you realize, there might be a few overlapping timestamps. And so, but it's mostly in order already, but there's just a few. And then insertion sort will actually sort everything in the right order quickly. So NumPy sort is just quicksort. It will be the best of the choice 99% of the time. And 99% of the time, you probably have enough computational power to never worry about this, right? It was a thing back in the 80s, and now we have all the most efficient algorithms that we can use. So unless this list is almost sorted. And so you can use heap sort and stable. That was not included in this. There are other options. There's also, I'm sure there are other algorithms already implemented in possibly other libraries in Python. But we have NumPy sort, so we can actually sort our data. I'm just going to whack the spacebar. All right. One important thing is copy versus deep copy, right? So This is not a deep copy. Any changes in B are now also reflected in A. So it's because the equal sign basically points to the memory part that Python is using. And so I've initialized it here, but now B also points to the same thing. Any changes in B, I multiply B, or I don't know, sort B, then A is suddenly sorted as well. This is not a good way to do things to A, because you'll forget that this happened. So you want to use NumPy copy in order to make an actual physical copy of the data. It's so no longer a shared pointer, so now B is its own separate thing. So you can, for instance, sort B and then compare it to A, which is not sorted, right? So you can smooth B and compare it to A and see what, then you can actually do operations on it again. So it's actually a good idea to use NumPy copy. So copy versus deep copy. And so is it a normal bug, or is it a get the lighter fluid kind of bug? It's not a bug altogether now. It's a feature. So all these things reflect choices of the people who developed the language. And they had good reasons to make that choice, but the choices are different. One of those example choices is starting counting array indices at 0. You have the first one is called 0 and then onwards. That is a choice. That's not a bug. If you run into it, it is not a bug. It's a feature. And I'll repeat this over and over again. If you get annoyed at it, it's like, yeah, but it's not a bug. It's a feature of the language. And so why is that like? It's because it's a pointer. And so it allocates, you only allocate array when you need it. And you can deep copy your data over and over again, but at some point, your machine will start to struggle because you are basically assigning new memory to every time you copy it. And maybe you don't need it. Sometimes there's a good reason why you should do it, where you're like, well, I want to compare the data against an something that I applied operations to, and then compare the two. That's a good reason to use a deep copy. But oftentimes you don't need it. So everything is a pointer in Python. Remember that. File I/O, right. Here's a NumPy native file input-output module. It's called gen from text and save text. This is the most basic way to get data into your Python Jupyter Notebook or Python code. Gen from text is generate from text, and it needs a few little things saying like, yeah, expect a CSV file or something like that. Save text does the same thing. It saves it to a plain text file. Plain text files are great. They're wonderful. A lot of my data is in plain text files. If you are dealing with megabytes or terabytes of data, plain text files are not your friend. And so when we get deeper into data ingestion, we'll talk about modules like AstroPy ASCII or AstroPy tables especially, and the pandas package, which are basically set up so that you can ingest millions of entries or billions of entries without, I don't know, really waiting for this thing to chug along. A text file with a million entries is just unreadable and also hard to handle. But table files or data files, there are packages to deal with that stuff, and they have packages that use operations on all that stuff, so you can actually do it much quicker. But NumPy is a good way to start, and if your data file is 100 or so, it's great. It's wonderful. You never have to leave NumPy. So file I/O for everything can be done with text files. But again, I use text files. No problem with text files. Text files are great. But you need metadata, you need column information, and that stuff becomes critical and really convenient if you actually have it saved in the data itself. There are many, 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 many different ways that you can save data. This is, again, there's always an XKCD for that, right? So text files, CSV files, PDF and TeX are not really data files. I'm not sure what some of those are. PNG obviously is an image file, but that's also data. JPEG is a compressed image file, also data. And .gif is an uncompressed data file and image file, and therefore also data. So you can actually ingest stuff You can ingest other kind PNGs, and we'll do that in a bit, JPEG, and then other images. Images are great data. Images are data that we work on. So honestly, this is very, very close to the truth. I really distrust anything that is like a PowerPoint file. I go like, oh, what's that? But it means that we have lots of different standards. Our data can come in all kinds of ways. Even the text file. Did you use a space, a tab, or double space to separate column A from column B? That's a choice, right? Again, not a bug. It was a feature of your data. And that's just text. And so standards, like this is how you format the data. A typical example is here's an Excel sheet. This is where you should put in your hours, right? So that's a typical example of a data standard. And so it essentially means that a whole subfield of physics or a whole subfield of sociology basically says, right, we want to be able to swap data easily, and we want to be able to read what it says, so here's the standard. And I talked about FITS files, and that was essentially astronomy's way of saying, all right, well, we need a standard. We need a standard that has metadata, like where was it observed, what exactly were you looking at, what kind of coordinate system were you using, all that stuff, plus the image, right? So that's a fantastic way. Like, yeah, it caters to our needs. But then you're a particle physics and go like, what's a FITS file? And so you can't use that data. And so having more and more standards actually is something. This is how standards proliferate, right? There's 14 competing standards. There's 14 different ways to save data. And then usually when people get together and go like, oh my gosh, they're all terrible and it's so hard to exchange them. We should just have a common standard that actually brings everything together. And then we're using 15. This is how it happens, right? How do you save images, and how do you exchange images with people, right? So how do I send a picture, how do I send my selfie to you, right? It is the kind of thing where you go, is it a JPEG, is it a PNG, right? Can my readers actually deal with a JPEG or a PNG? And that's just, or GIF, or GIF, whatever you want to call it. But essentially, those are 3 image standards. There's no good reason why we have 3 or more, but this is kind of what happened. Right? We already have 2 kinds of JPEGs, and it's just, it's a mess. So we have a standard data ingestion. So we can go from NumPy import gen from text, or my preferred way in data is np gen from text myfile.csv in the delimiter. And the delimiter is the important thing, right? What I just talked about, like, is it spaced with tabs? Is it spaced with spaces? Is it spaced with commas? A comma-separated value file means a delimiter is the comma. All my data doesn't have a comma in it. There's just periods or text or something, but I've agreed with myself that whatever my strings hold, they don't hold commas, right? So I'm not using commas for anything else except to space the columns. And so why do this any other way? Well, units. Remember, we're physicists, and we want units. My data has units. If your data doesn't have units, I don't trust your data. And so every column has a name. That's a better way to actually exchange data files with somebody. If you go like, yeah, it's column 122, or was it 123? That's a long afternoon. So giving everything a clear name in the columns. And I said 122. That's not an exaggeration. Data files with hundreds of columns are not that weird. So saying, yeah, you need Stella Mass or the Stella Mass _ error, which is the error bar, right? So these are things that are communicate what's what easier, and just naming each column gives you instantly access to that column. But this will just give you the lists of numbers. So yeah, you'll have to say, you need to be in column number 122. So CSV files are comma-separated values. How I think of your data, I think most of your data will actually arrive to you. It is a fairly easy way to edit data. It's a fairly easy thing to export from Excel or Google Sheets or Mac Numbers if you're using that. So it's something that you can inspect in Excel, Google Sheets, or Mac numbers. CSV files is what we're expecting most of the time. And you can have a little header where you put the names of each column, and maybe in the second row we actually put the units. And then you just say, ignore the first two rows because that has the meta information in it, and everything else is just a field of rows and columns. So that's wonderful, right? So that's how I sort of expect your data to arrive. Who knows? That's what I'm expecting right now because most people work in Excel and most people are at least export CSV files, but there might be other formats. I like this because often we can also share a Google Sheet and, for instance, add a column with our comments for each measurement, for example. So it's easy to add to that. So why am I not teaching you Google Sheets or Excel tricks to do your data analysis? Because all these things are basically meant for spreadsheets, for financial spreadsheets. So they're great at adding everything up in a column. And they're great at finding the average earning or something like that. But there are a whole bunch of statistical tests and tricks that Excel simply doesn't have. Not on knock on Excel. If you're good with that, great. But the kind of data analysis that I want to do, the kind of visualization I want to do, often we need just that extra bit more. And then trying to figure that out in Excel, and then realizing that, I don't know, the kind of fit that you want to do to data other than linear is not available is, frustrating. So I know this stuff is here in Python. So read all the standards. Well, read all the standards in your field. So for astronomy, we use AstroPy ASCII or mostly AstroPy tables. So that ingests a CSV file and puts it in a table format, which already has column names named and remembers what units they are. There are other tricks we can do, and AstroPy has different ways that it can then format them, for example. The pandas package is much more generally used. So if you have a Windows machine and you couldn't install AstroPy, you can also use pandas. And the Python data analysis library, Panda, or something. They definitely wanted to end up on pandas. So pandas is a way to do data science. That's the data science package for Python. So it's very much optimized. You have giant tables of patient information. Great. Well, we'll help you ingest it, attach them, select from it, visualize them out. Pandas is the data science library. AstroPy does a bunch of astronomy stuff as well. Doesn't blink if you give masses in solar masses, for example. So that was this week. We talked about all the casting and all the operations we can do. So we can get our data, we can ingest our data, and we can figure out what our data looks like. We can figure out the shape of our data. We can figure out the statistics of our data. We can get a first feel. We can turn it into some numbers. That's what we've got so far. But then, the first thing you do is you have to look at the data. Instead of staring at a giant table, we need to visualize it out, right? So these are the things that we're going to do next week. I'll introduce you to Matplotlib, which is one of multiple visualization packages in in Python. Matplotlib is the standard. And for 99% of your usage, Matplotlib will be perfectly fine. And that's the 5th Jupyter Notebook assignment. So at the end of this week, I expect Jupyter Notebook assignment number 4 to be handed to me in Blackboard. So I'm looking forward to those.